Hello dear students. The chapter of general physiology has four distinct segments. First, we will begin with body fluid compartments. After that, we will take concepts in physiology like homeostasis, milo-interior, positive and negative feedback, and so on and so forth. Then we will discuss the cell membrane structure, what all components are present in the cell membrane. And then the last segment would be transport through the cell membrane, how the substances enter the cell, leave the cell, and so on. So these distinct four segments in which we will discuss the general physiology chapter, and therefore let's start with the first one, and that's body fluid compartments. We will discuss this in three small segments. First, we will describe volumes of the various body fluid compartments, the ICF, the ECF, the interstitial fluid, plasma, and so on and so forth. So what are the various volumes of these compartments? Second would be, how do we measure them? Measurement of the body fluid compartments. What are the various methods? What are the various indicators used to measure these body fluids? And the third one, of course, every chapter ends with the application of that. So here we will discuss disturbances in the body fluid compartments. What if the fluid is lost? What if the fluid is gained into a certain compartment? So these will be the sections in this particular topic. Let's begin with this chapter, body fluid compartments. Let me just at the outset tell you some questions which have been asked in the various entrance exams. For instance, one question was repeatedly asked, that is, 10 grams of mannitol was injected to measure the volume of the ECF, extracellular fluid volume. It got uniformly dispersed into the ECF, and then when the sample was collected for the concentration of mannitol was found to be 50 milligram %. And from the initial injection, 10% volume of the mannitol was lost out of the body. So this was excreted out of the body, and this is the data given, and they ask what is the volume of the ECF, or they can ask what is the volume of the interstitial fluid, 5 liters, 12 liters, 15 liters, 18 liters, 5, 12, 15, 18. That's one question which has been asked repeatedly. Second question which can be asked from this particular section is an image-based question. They give you an image which depicts the body fluid compartments like this. They give the volumes of the ICF and ECF, and the disturbance is shown diagrammatically. This is a diagrammatic representation of the disturbance that is going to happen. So shown in the red lines is the normal volume and osmolality of the body fluids, and the shaded area shows the disturbance, and therefore what kind of disturbance is this, or what is the condition in which this is likely to happen. And the options given are diabetes insipidus, SIADH, primary hypoaldosteronism, or administration of hypertonic saline given IV. These are the options given, and you have to select the correct one. So we are going to discuss all this in detail and also solve the MCQs. Let's start with the first section, that is volumes of the various body fluid compartments. The prototype man will be a 70 kg healthy adult. So in a 70 kg healthy adult, what would be the volumes? First thing, total body water is 60%, approximately 60% of the body weight. So 0.6 into the body weight is the volume of the total body water, 60% of the 70 kgs, and therefore it would be 42 liters. That's the total body water. Now, out of this, 2/3 is ICF and 1/3 is ECF. 2/3 is intracellular fluid, 1/3 is extracellular fluid or in the extracellular compartment. Or we can say intracellular fluid is 0.4 into body weight and extracellular fluid is 0.2 into body weight. Right? 0.6 into body weight is the total body water, and 2/3 is ICF, 1/3 is ECF. Therefore, ICF 0.4 into body weight, ECF is 0.2 into body weight. And so, out of these 42 liters, of course, 28 liters would be intracellular fluid and 14 liters would be the extracellular fluid. Clear? 14, 28, 42. Just remember these figures. 14, 28 and 42 is the total body water. So whenever, I would just reiterate this fact here, that whenever you see certain figures, it should strike that particular component to you. If you say 14 liters, immediately what should strike you is this is the volume of the ECF. Right. Going into further details, ECF has, of course, two components, the interstitial fluid and the plasma. So, out of this total 14 liters, 3/4 is interstitial fluid and 1/4 is plasma volume. That means out of this 14 liters of the ECF, 3/4, I would say roughly 11 liters would be interstitial fluid and 3 liters would be plasma volume. So that's ECF volume. If you take total blood volume to be 5 liters, out of that 3 liters would be plasma, 2 liters would be cell. That's an approximate proportion. Looking at it from another point of view, for example, blood volume is 8% of the body weight. So, in a 70 kg healthy adult, 8% of that 70 kg is roughly about 5 liters. And out of that, plasma would be 5% of the body weight and cell volume would be 3% of the body weight. So remember, blood volume is 8% of the 70 kgs or whatever body weight given, and plasma volume 5% of the body weight. Remember, in neonates, in small children, there are certain variations, and the difference in the surface area to volume ratio compared to adults. So a higher surface area to volume ratio, and therefore they are more prone to dehydration. Remember, children are more prone to dehydration. Their ECF volume will deplete and they will be more prone to dehydration. We will see all these things later on in the chapter. Okay, So these are the volumes of various body fluids. The second part is measurement of the body fluid compartments. How do we measure them? And even this has been asked repeatedly in various entrance exams. Radio labeled albumin is used to measure which volume, which body fluid volume. Is it the ICF? Is it the interstitial fluid? Is it the plasma? Or is it the entire ECF? Of course, the answer is plasma. We will see why and how. Okay, so let's begin. How do we measure the various body fluids? The method is called dye dilution method or indicator dilution method. Indicator dilution method is based on the Stewart-Hamilton principle. I mean, it is named after Stewart Hamilton. So sometimes also called as Stewart-Hamilton dye dilution technique. What is the basis for this particular technique? It's a dilution of the indicator. Let's say a known volume of the indicator is going to be injected into a compartment that we measure. A known initial volume I, a known initial volume I of that indicator is injected into a particular compartment. It should stay in the compartment. The prerequisite is that it should not leave the compartment. Suppose I am measuring ECF volume. It should stay, this indicator, this dye should stay in the ECF. It should not enter the cells or it should not get excreted out of the body. It should remain in the compartment. And the second prerequisite, more important, it should get uniformly distributed throughout the compartment. Uniform dispersion into the entire compartment. Once it gets uniformly distributed into the compartment, then I take a sample from the compartment and measure the concentration of that dye. C is the concentration of that indicator. Once it got uniformly dispersed into the compartment, the concentration, that is C, is measured. Concentration of the dye or indicator will be measured. And then I can measure, I can calculate the volume of a particular of that compartment where we injected the dye. V, volume of the compartment, is equal to I upon C. I is the initial volume of the dye injected. Initial volume that was injected into the compartment, then it got uniformly dispersed, and then we collected sample and concentration was measured. So C is in the denominator, concentration of the dye after it got diluted. Remember, we called it dye dilution method. So that's how it can be calculated, the dilution of the dye, from the extent of dilution of the dye. Let me just, for the sake of making it little simpler, let's take an example. Suppose this is the initial volume of that dye. This is just a diagrammatic explanation, all right, to make you understand this particular method. Suppose this is the initial volume of that dye or indicator which we are going to inject into the compartment, and there are these two compartments. Suppose this is compartment A, this is compartment B. These are the volumes of those compartments which I will measure, and same initial volume I, if I inject into compartment A and compartment B, what do I see? What do I get? In compartment A, see, the volume of that compartment is high. greater volume. So this dye will get diluted to a larger extent, to a greater extent, and therefore, see, I've put it into this compartment, it will get dispersed and diluted to a much greater extent. And in compartment B, volume of the compartment is less. Therefore, dilution of that same amount of dye will be less there. So if I collect the samples from the compartments, what do I get? Concentration of this dye, concentration of the dye in this compartment A is going to be less. Concentration will be less because the dye got diluted to a greater extent. Greater dilution means less concentration, right? And therefore, less the concentration of the dye, that means more will be the volume of that compartment. Volume of the compartment is large. So you see, C, the concentration of the dye, is in the denominator. Less the concentration, less the denominator means greater will be the volume of that compartment. We can see here from this example. So that is how we can calculate the volumes of the. Of course, one more issue is there. What if after injecting, some of the dye leaves the compartment? Then what do we take there? Okay, the equation will then become V is equal to I minus A upon C. This should be the final equation. A is amount of the dye that left the compartment after initial injection. A is amount of the dye that leaves the compartment after the initial injection. So take this as the final equation. We are that amount should be done minus from the numerator itself. Okay, that's how we calculate volumes of the various body fluid compartments. Let us solve the MCQ, which I mentioned at the beginning. 10 grams mannitol was injected initially. So initial volume of the dye injected was 10 grams. And then after it got dispersed into the compartment, concentration, a sample was collected from the compartment for the concentration of the dye. It was found to be 50 milligram %. And then I also mentioned that after initial injection of mannitol, some 10% was excreted out of the body. So A was about 10%. 10% of 10 grams. That means 1 gram was lost out of the body after initial injection. Okay, so what will be the volume of the interstitial fluid, or what will be the volume of the ECF? Let's put the values here. V is equal to I minus A upon C. That's the equation. So volume of the ECF will be equal to 10 grams minus 1 gram upon 50 milligram %. 9 grams upon 50 milligram %. Okay, so the answer is 18 liters would be the volume of the ECF. And let's just complete it. 9 grams. Let me just make a point here, small point which we often tend to forget. The units are not matching here. Look, this 9 grams or the 10 grams which was injected was into the liters of the body fluid. Okay, so numerator is per liters and denominator is milligram %. Milligram % means milligram per 100 ml. So we will have to now match the units first for numerator and denominator. What would it be? 9 grams is 9000 milligrams and denominator 50 milligram % means 500 milligram per liter. We will have to see numerator is into numerator was mannitol injected per liter of the ECF. So numerator is in per liters, denominator should be in per liters. 50 milligram percent means 50 milligram per 100 ml. Convert it into per liter, that will be 500 milligram per liter. And now 90 upon 5, the answer is 18 liters is the volume of the ECF. That's the answer to that particular question which I asked at the start. And if I were to divide it further, remember 3/4 is interstitial fluid and 1/4 is plasma. So if the question was what will be the volume of the interstitial fluid, roughly 14 liters would be the interstitial fluid and 4 liters would be the volume of plasma. That was how it was expected to be solved, that particular question. Right. So that was about dye dilution method and the equation. Now let us see what indicators are used. What are the various indicators which are used for this method? Okay, total body water. What should be the criteria for an indicator to be used to measure these various compartments? Let's look at them one by one. Total body water. Look, for the dye dilution method, the sole criteria is that the dye should uniformly disperse into that compartment which we are going to measure. So, if we are measuring total body water, which includes all the body fluids, in fact, I mean it should be going into the ECF, ICF. I may just add in our previous data which I mentioned to you, there is 1 liter of the ECF volume which is also called as transcellular fluids, like a aqueous humor or a synovial fluid or a pleural fluid and so on. So these are that's a transcellular fluid, about 1 liters. 1 liter fluid is transcellular fluid, which includes synovial fluid, aqueous humor and such fluids. Anyways, the point was that whatever we are going to measure, whether it is total body water, which includes ICF, ECF, all the volumes, or we are measuring ECF or whatever, the dye should uniformly distribute into that compartment which we are measuring. So if we are measuring total body water, what should be the criteria for it? The criteria should be that it should easily cross the membranes. The dye that should be used, that we are going to use, the criteria is that it should easily, the membranes should be non-existent for that dye. Only then it can cross the membranes and mix in all the compartments, because we are measuring total body water. That includes all the compartments, right? So the criteria for measurement of total body water, the criteria for the dye is that it should cross the membranes easily. So what are those indicators? Deuterium oxide or tritium, antipyrine or aminopyrine. These are the indicators for measurement of total body water. Then second, ECF volume. How do we measure the ECF volume? Non-metabolizable saccharides are used to measure the ECF volume, because we inject these into the ECF, they should not enter the cells, and if at all, they should not be metabolized also. Non-metabolizable saccharides are used to measure the ECF volume. The best that suits this is the inulin. So remember, this question has been asked repeatedly in various entrance exams. The best substance to measure the ECF volume, inulin. very often the students make a mistake of inulin and insulin. I've seen that happening. Inulin is a polymer of glucose, or it's a fructopolysaccharide. Fructopolysaccharide. It stays into the ECF. It hardly enters the cells. It does not get metabolized, and it's the best. But there are others like mannitol. We mentioned it already. Sucrose. So remember, ECF volume is sometimes called as sucrose space. Remember this. There was a question like this. In a person, his sucrose space was found to be X and his deuterium space was found to be Y. X, Y. What will be his total body water? Or, okay, not total body water. The question was, what will be his intracellular volume, ICF volume? We will come to that in the next 30 seconds. We have seen total body water. We have seen ECF volume. So what is left? The ICF volume. ICF volume cannot be measured directly. It is measured indirectly as the total body water minus the ECF volume is the ICF volume. Naturally, right? And so the question that I asked you just now, if the deuterium space is X and the sucrose space is said to be Y, then ICF volume will be X minus Y. Total body water minus the ECF volume. That will be the ICF volume, intracellular fluid volume. Okay. Plasma volume. How do we measure the plasma volume? What is there in the plasma? The plasma proteins, albumin, and therefore radio labeled albumin is used to measure the plasma volume. Iodine isotope is used for this purpose. Okay. The basis remains the same, that a known quantity of radio labeled albumin will be injected into the plasma. It will get dispersed into the plasma proteins, and then we will collect the sample and measure the dilution of that radio labeled albumin. And red cell volume, can we measure the red cell volume? Well, red cell volume is the packed cell volume. Normally it's a hematocrit or packed cell volume. We can measure that way. Is there any method in this? Yes, it's there. Chromium 51 tagging of the red cells. Look, normally the volume of the red cells is packed cell volume, or hematocrit it's called. But I'm saying by this dye dilution method or the principle can be used for measurement of the red cell volume in the body. A known fixed quantity of red cells or number of red cells will be tagged with chromium 51, and they will then disperse into the red cell volume, and from the dispersion we measure the volume of the red cells. Volume means the packed cell volume, volume of all the red cells packed together. Okay, so that's how we measure the various body fluid compartments. I told you the formula, the method, the substances used, and that brings us to the third point, and that is disturbances in the body fluid volumes. Let's first understand the basic principles of these disturbances. A disturbance is of two types. There can be dehydration condition, where the volume is lost out of the body, or overhydration. Overhydration is volume expansion. Volume will be gained, fluid will be gained. So these are the two types of volume disturbances. Let's take them one by one and also talk about their principles as to what happens in that particular condition. Dehydration. Volume is lost. Now I'll tell you the basic for both of them. The common basic principle is whether volume is lost or volume is gained. In the case of overhydration, it is from the ECF primarily. Volume lost or volume gained is primarily from the ECF, extracellular fluid. And then if the osmolality of the ECF gets altered, then there will be a secondary movement of water from the ECF to ICF or ICF to ECF. And accordingly, there will be secondary changes in the ICF volume also. But there will be secondary changes, okay? I repeat once again, and I am going to describe it with examples. So don't worry. Right now, just listen to the primary basic principles of these conditions. Whether it's dehydration, whether it is overhydration, primarily it happens from the extracellular fluid. Loss of water from the ECF or gain of water into the ECF. Dehydration or overhydration. Accordingly, if the osmolality of the ECF gets altered, then there will be a movement of water from the ECF into the ICF or from the ICF into the ECF, because they need to be in osmotic equilibrium. I am going to take the example, okay? So don't you worry at all. We will discuss this with example and then it will be amply clear. So let's take the examples. Whether dehydration or overhydration, it will be of three types: isotonic dehydration or hypertonic dehydration or hypotonic dehydration. Similarly, isotonic overhydration, hypertonic overhydration or hypotonic overhydration. Let's see. Without wasting any further time, let's go to the example straight away. Isotonic dehydration. First type of condition, isotonic dehydration. Let's have a diagrammatic representation. Look, 28 liters is the volume of the ICF, 14 liters is the volume of the ECF. So it's quite clear that on horizontal axis there is volume of the compartment. This is the ICF, this is the ECF. And 300 milliosmoles per kg of water, osmolality. So 300 is the vertical axis is the osmolality or tonicity of the compartments. Now isotonic dehydration, first condition. How will it look? It will appear like this. Shaded area tells you the story of that condition. Remember, this is the isotonic dehydration. What is this diagram telling you? The diagram tells you that the volume has been lost from the ECF. Okay, volume has been lost from the ECF. So ECF volume has shrunk. You can see here on the horizontal axis. But there was no change in the tonicity of the ECF. And therefore, no shift of water from ICF to ECF or ECF to ICF. This is isotonic dehydration. Just simply dehydration, but it remained isotonic. Right. When does that happen? Now imagine water was lost from the ECF. Water was lost from the ECF, but sodium also was lost from the ECF. Sodium and water. Sodium lost, water lost. Both were lost in the equal proportion. What will be the result? The tonicity will remain the same for the ECF. That is what has happened. No change in the tonicity. So, When does this happen? This happens in GI fluid loss, burns, hemorrhage. In burns also, it is said that there is a loss of fluid and sodium into the so-called third space, or as the skin is denuded, there is loss of water and loss of salt in equal measure. That was isotonic dehydration. Second, hypertonic dehydration. Hypertonic dehydration. This is easy to understand. Hypertonic dehydration. Now look at this, how it will appear on the diagram. 28 liters, 14 liters, 300 milliosmoles per kg of water. That's the tonicity on the vertical axis. Hypertonic dehydration. What does it mean? Only water was lost from the ECF. Only water was lost from the ECF. See, this is sodium, this is water. Only water lost from the ECF. So in the ECF now there is more sodium and less water. That means ECF becomes hypertonic, isn't it? Okay. So water lost from the ECF, and since only water was lost, ECF becomes hypertonic. Now listen to the second part. Because ECF is hypertonic now, more sodium, less water, therefore there will be shift of water from ICF to ECF, because ECF, extracellular fluid, is now hypertonic. So it will pull water from the ICF. Water will move from ICF to ECF because ECF has become hypertonic. Water will move from ICF to ECF, and therefore ICF volume will shrink secondarily. There will be a secondary shrinkage of the ICF volume because ICF water came out into the ECF. So the diagram will have to appear like this. Finally, they will go into osmotic equilibrium. Look at the shaded area. See, ECF volume has decreased, dehydration it is, therefore it's and since only water was lost, ECF became hypertonic. You see, 300 is the normal tonicity of the plasma or ECF. This is hypertonic, and because ECF was hypertonic, ICF water will move into the ECF so that they finally reach osmotic equilibrium. But because of that, ICF volume also has shrunk secondarily, which you can see here, 28 liters. The volume has shrunk. Right, so that was hypertonic dehydration. Now, when does that happen? What are the conditions? All those conditions in which there is osmotic diuresis or water diuresis, and simply water is lost out of the body, such as diabetes mellitus, diabetes insipidus. Diabetes insipidus would be a deficiency of ADH, and therefore there would be diuresis and water will be lost into the urine. Chronic alcoholism. In chronic alcoholism, there is a water diuresis and only water is lost. Excessive water loss. Chronic administration of lithium salts. This is also known to cause hypertonic dehydration. Now then, the third one, hypotonic dehydration. Hypotonic dehydration. Look, dehydration it is. That means water loss from the ECF. Now imagine, this is sodium, this is water. Water is lost from the ECF, so it is dehydration. But sodium loss is much more as compared to water loss. And now what happens as a result? Less sodium, more water. See, sodium, water. This is the isotonic ECF. Now water is lost. So this is dehydration. But sodium loss is much more. Even greater sodium loss is happening. Therefore, this is now, what is the eventuality? less of sodium now in the ECF and more of water. ECF is now hypotonic and dehydrated. So hypotonic dehydration happens because of this kind of a loss. How will you show it with the diagram? So here we go. 28 liters, 14 liters, 300, that's the osmolality. Now dehydration. So ECF volume decreases. This is a dehydration. And ECF is hypotonic. And if ECF is hypotonic, you know what will happen? ECF water will shift into the ICF because ECF is hypotonic. So ECF water will shift into the ICF. That means ICF volume will increase secondarily till they reach the osmotic equilibrium. You can see in the diagram, in the shaded area, of course, it's a dehydration, volume has shrunk and tonicity of the ECF has also decreased. So this is hypotonic dehydration. And because ECF was hypotonic, the ECF water will shift into the ICF. So ICF volume, you can see here volume is on this axis, ICF volume will increase secondarily till they go into osmotic equilibrium. This is the osmotic equilibrium. So that's hypotonic dehydration. Now the question is, when does this happen? It happens in primary hypoaldosteronism or primary hypoadrenocorticalism. Adrenal cortex insufficiency primarily, and therefore there is decreased secretion of aldosterone. Now look, what is the function of aldosterone? Aldosterone reabsorbs sodium. That's primarily the job of aldosterone. It reabsorbs sodium, and therefore with sodium there will be movement of water also from the renal tubules. In the case of hypoaldosteronism, if there is lack of aldosterone, sodium will not be retained, reabsorbed. That means sodium will be lost into the urine. So sodium, water, sodium loss, water loss. But sodium loss will be much greater. You know, sodium pulls water by osmosis. So even this is a renal tubule. Aldosterone was expected to reabsorb the sodium and some amount of water also by osmosis. Now this is not happening. So sodium lost into the urine and therefore some amount of water also lost into the urine. That is the condition. So these were dehydration conditions. Let us look at the other end of the spectrum, overhydration. Volume expansion. Volume expansion states water is gained, and again there will be three types: isotonic overhydration, hypotonic overhydration, hypertonic overhydration. Right. First one, isotonic overhydration. How will it look in the diagram? Right, so 28 liters ICF, 14 liters ECF, 300 is the tonicity. Isotonic overhydration. Look, it's a overhydration, so ECF volume will increase primarily. Yes. And since ECF is isotonic, there would not be any shift of water from ICF to ECF or ECF to ICF. So ICF volume will not change secondarily. This is isotonic overhydration. You can see ECF volume has increased volume on the horizontal axis, but tonicity hasn't changed for the ECF, and therefore no secondary shift of water. So when does that happen? Administration of oral or IV isotonic saline. Isotonic saline given oral or IV. Second, hypertonic overhydration. Hypertonic overhydration. Administration of oral or IV hypertonic saline. This will result in hypertonic overhydration. And how will it appear in the diagram? So here is 28 liters, 14 liters and 300 hypertonic overhydration. Look, first of all, overhydration, that means volume, ECF volume has increased and ECF becomes hypertonic. So because ECF is hypertonic, ICF water will shift into the ECF. ICF water will shift into the ECF because ECF has become hypertonic. And therefore ICF volume will shrink as a secondary change. You can see here, diagram will appear like this. Shaded area, I repeat again, shaded area shows the changes in those compartments, or the entire condition is shown by the shaded area. This is hypertonic overhydration. So it's simple. Suppose in an exam, you will get this diagram and you will be asked what this condition is. You have to see what is happening to the volume of the ECF. There, it's increased. And you have to see what's happened to the tonicity of the ECF. It's more than 300 or less than 300, or it's just isotonic, it's just 300. So, and then you can answer the question accordingly. And the last one is hypotonic overhydration. Hypotonic overhydration. Meaning what? Only water conserved into the ECF, only water gained into the ECF, water and water. Because water was gained into the ECF, it will be overhydration naturally, okay? And since only water has come, no sodium, only water was gained into the ECF, ECF becomes hypotonic. Yeah, this is sodium, this is water. Only water is being gained into the ECF, water is increasing. So what will happen? Less sodium, more water into the ECF. ECF becomes hypotonic and overhydrated. Let's see the diagram and then also discuss the condition in which it appears, it happens. Here is 28 liters, here is 14 liters, 300. Okay, overhydration. So ECF volume has increased. But since it was only water gained into the ECF, ECF became hypotonic. You can see there, hypotonic ECF. And because ECF is hypotonic, what will happen? ECF water will shift into the ICF so that they reach osmotic equilibrium. That means ICF, there will be a secondary increase in the volume of the ICF also, because ECF was having more water, it was hypotonic, and therefore its water shifts into the ICF, so ICF volume has increased secondarily and they reach osmotic equilibrium. This was the diagram which I asked in the beginning. So the condition was hypotonic overhydration, hypotonic overhydration. You can see on the ECF side, overhydration and hypotonicity. and then secondary change in the ICF volume. Okay, now the question is, when does this happen? This happens in the condition of SIADH, syndrome of inappropriate ADH secretion. Yeah. Now, first of all, why we call it inappropriate ADH secretion? Look, ADH is the hormone which is going to primarily regulate our osmolarity of the plasma or osmolarity of the ECF. And therefore, when does it come into action, the ADH? When the plasma becomes hypertonic. When the ECF becomes hypertonic, the ADH will come, and ADH will cause water reabsorption. Water will be taken into the ECF. ECF was hypertonic. Now water has come. That is, the ECF osmolarity will be normalized. You understand that? Whenever the ECF is hypertonic, we will need water to be gained into the ECF or into the plasma. That is the time when ADH is secreted and it causes antidiuresis, it reabsorbs water. So that's the normal ADH secretion. When I say SIADH, syndrome of inappropriate ADH secretion, I mean that plasma osmolarity was normal and yet ADH was being secreted. ECF tonicity was normal. There was no need for ADH secretion, yet it is going on getting secreted. That will be inappropriate ADH secretion. So this happens in various conditions like surgery, like stress, anxiety, fear, and so on and so forth. And because plasma and ECF were already normotonic and ADH is coming and causing further water retention, what will happen? Volume of the ECF will increase, and now excess water into the ECF means ECF will become hypotonic. Excessive water has been gained. Okay, so that's inappropriate about it, and hypotonic overaddition. But let me extend this a little further. ADH is the one who regulates osmolarity of the ECF, right? Means suppose ECF is hypertonic, more sodium, less water. So ADH will come, ADH will gain water, and plasma tonicity will be normalized, right? If it is hypotonic, plasma is hypotonic, means less sodium, more water, then ADH will be suppressed, ADH secretion will be suppressed, so there will be diuresis and water will be lost out of the body, and then ECF becomes normotonic. So it's the ADH, the job of the ADH is to control the osmolarity of the ECF and the plasma. Now there is inappropriate secretion of ADH. So who will regulate the tonicity then? What happens is, under this condition, since it is overhydration, since it is increased volume, circulating blood volume has increased, plasma volume has increased, there is increased filling of the atria. Right atrial filling will increase, and the stretch of the atrial musculature, because blood volume, circulating volume has increased, stretch of the musculature, and then there will be release of ANP, atrial natriuretic peptide, atrial natriuretic peptide. This will be released. It will from the atria, it will go to the kidneys, and it will cause natriuresis and diuresis. Natriuresis, sodium loss into the urine, and water loss into the urine. So that excess water which was present, it will be lost. Final point that I am trying to make here is this. Remember, when SIADH was the starting condition, that is what was happening, and sodium and water in the ECF. Now water has been gained because of inappropriate ADH secretion. This initially resulted in dilutional hyponatremia because there was a lot of water into the ECF, lot of water into in the plasma, and therefore more water and relatively less sodium. Look, it's not really less amount of sodium. Sodium is less relative to water. More water, therefore less sodium. That's dilutional hyponatremia. Because of the dilution of the ECF, relatively it's the less sodium. But then that was a starting condition. What will be the end result? Water has been lost. Yeah, there is diuresis. Because of the ANP, there is natriuresis, loss of sodium into the urine, and there is diuresis, loss of water. So now water has been lost. So volume returns to normal. ECF volume will return to normal. But there is also loss of sodium. Therefore, now the condition will be euvolemic hyponatremia. So please remember, SiADH starts as a dilutional hyponatremia, and the end result, because ANP was released as a counterbalancing hormone, the end result would be euvolemic hyponatremia. So that's the disturbances in the body fluid compartments. Just last one question, and then we will end this particular section. A man was on a voyage, and by mistake the man drinks 1 liter of seawater. What will happen to this man after 1 hour? The man drinks 1 liter of seawater. So what will happen to him after 1 hour? And the options are hypertonic overhydration, hypotonic overhydration, or hypertonic dehydration, or hypotonic dehydration. So first of all, you have to decide whether this will result in overhydration or dehydration, and then it will you have to decide whether it will be hypertonic or hypotonic. So what's your opinion on this? I'm sure you are thinking of overhydration as a starting point, because look, some time back we saw that if orally hypertonic saline is given, then it will result in hypertonic overhydration. Yes, that's right. So you are thinking of overhydration because seawater is a hypertonic fluid. Cool, no problem. It's a hypertonic fluid given orally. Now there is some catch in this. That is why this question was asked. Look, the osmolarity of seawater is 1200 milliosmoles per liter. The osmolarity of seawater is 1200 milliosmoles per liter. So when a man consumes 1 liter of seawater, he has consumed 1200 milliosmoles of solute. Okay, it's a hypertonic fluid, but it's a hugely hypertonic fluid. And what are the consequences? One critical fact that okay, let me just make a correction. Just correction here. The osmolarity of seawater. Make a correction. The osmolarity of seawater is 2400 milliosmoles per liter. 2400 milliosmoles per liter. That's the osmolarity of seawater. So when a man consumes 1 liter of seawater, the man has consumed 2400 milliosmoles of solute. Okay. In 1 liter, there are 2400 milliosmoles of solute. And we are assuming in this particular MCQ that all those solutes will be absorbed from the gut and they will go to the kidney for excretion. They are all excretable solutes to be excreted. Now, one key factor that you should know in this is what is the maximum concentrating ability of the kidney. Maximum concentrating ability. This you should never forget. Maximum concentrating ability of the kidney is 1200 milliosmoles per liter. Yeah, just remember like this. Plasma osmolality is 300 and roughly 4 times that is 1200 milliosmoles per liter is the maximum concentrating ability of the kidney. Means how much maximally concentrated urine can be generated and excreted. In 1 liter of urine, maximally 1200 milliosmoles of solutes can be excreted. That's the maximum concentrating ability. Which means what? Which means to excrete 2400 milliosmoles of solute, how much urine volume will be needed? See, in 1 liter, only 1200 milliosmoles of solute can be excreted. So, to excrete 2400 milliosmole solute, how much urine output will be necessary? 2 liters. Yes. And did you notice? The man has consumed 1 liter of seawater, just 1 liter was consumed, and 2 liters will be the excretion or output. 1 liter consumption and 2 liter output, that means what? 1 liter extra will be lost from the body. 1 liter water extra will be lost from the body. And therefore, this will result in dehydration. 1 liter was consumed and 2 liter was the urine output. So that means 1 liter extra is going from the body actually. So this will result in dehydration. And since extra water was being lost, the ECF will become hypertonic. Yeah, water was extra 1 liter will be lost from the body. So plasma or ECF will become hypertonic. So this will result in hypertonic dehydration. Now this will be confusing for you, because you will say on one end we said oral or IV hypertonic saline given, it resulted in hypertonic overhydration. And now we are saying that this hypertonic fluid was consumed, the sea water was consumed, it is resulting in hypertonic dehydration. So what, how do we reconcile the two facts? Remember it like this. For the sake of principle, just remember like this. This is just sake of principle. If the osmolarity of the consumed fluid is less than 1200 milliosmoles per liter, it will result in overhydration. Right? If the osmolarity of the consumed fluid is less than 1200 milliosmoles per liter, it will result in overhydration. I told you, oral or IV hypertonic saline, it will result in hypertonic overhydration. But if the tonicity of the consumed fluid is more than 1200 milliosmoles per liter, as we saw in this case, then that will result in dehydration. Okay, so please remember this basic principle when you solve such questions. Finally, they used to ask a few questions related, because I mentioned ANP, atrial natriuretic peptide. Some questions were related to that. We will discuss this in the chapter of heart and then later on in kidney. But since it was mentioned here, ANP is synthesized by what? Atrial natriuretic peptide. So, heart, atrium. But there were questions. BNP is synthesized by. BNP is brain natriuretic peptide. Synthesized by what? Heart, brain, lungs, liver. What's your answer? Brain, is it? No. Heart. The answer is heart. It's the ventricles which synthesize this BNP. It's called brain natriuretic peptide because initially in the experimental animals, this peptide was found in their brain slice preparations. but then in humans it's BNP, brain natriuretic peptide, also called as simply B natriuretic peptide, is synthesized by the heart. And finally CNP, C natriuretic peptide, that also is synthesized by the heart. I mentioned it here because somewhere while we're discussing SIADH, I had mentioned ANP, so atrial natriuretic peptide, and therefore I just quickly added the other two as well, which cause natriuresis, loss of sodium. So that was the first section of the general physiology, body fluid compartments.